Let's continue with chapter 10 and look at this hypothetical life table. Again, we've got our ages, or age stages. We have our survival rate, our survivorship, and our fecundity. Um, okay, so based on this information, um, we can determine the growth of this population through time. Um, so you can see that the survivorship rate for the first stage, that is from 0 to 1, is relatively low, 0.3. The survivorship for the next stage from 1 to 2 is higher at 0.8. But the survivorship from 2 to 3 is essentially 0. Individuals don't live past stage 2 to stage 3. And then this is our drop in fertility or survivorship. Of course, again, we said the survivorship rate for the first stage was only 0.3. So by the time they're 1 year old, only 30% are left. 80% from one stage, stage 1 to stage 2, so down to 0.24, and then down to 0. Okay, so here are those numbers. Here are those um, survivorship rates. And so if in this hypothetical population at given time period 1, or age x, we have 20 individuals that are born, 30 at stage 1, 50 at stage 2, and of course 0 at stage 3, giving us a population of 100. We know that the survivorship rate from being born to stage 1 is 30%, so 30% of 20 gives us 6 individuals that then survive to the next stage. Survivorship from 1 to 2 is 80%, so we have 24 that survive, and of course survivorship past then is 0. All right, so of these 100 individuals, essentially 30 of them survive to the next year. And those are the ones that reproduce. All right, so we see the fertility of individuals at stage 1 is 2 and stage 2 is 4. So 6 times 2 is 12, and then you've got 4 times 24. You sum those together, and essentially 108 individuals are born, okay, in the next time period. So from this year, with 100 individuals, to the next time period, the 6 and 24 that are surviving, plus the 108 offspring they have, gives us a population size of 138. So you can see the population has grown from essentially time 0 to time 1. All right, so what is the population growth rate of this population? Well, that's encompassed by this value we call lambda, the population growth rate. And lambda is essentially a function of the number of individuals at times t plus 1 over the number of individuals at times t, which in our case is 138 over 100, which gives us a lambda of 1.38. A positive growth rate, this is a growing population. Now, I want you to try to stop the video at this point and see if you can figure out what will be the population size and the number of individuals at each stage in the next time period. Okay, so what did you get? Well, all right, so of those 108 individuals, we know 30% of them survive, so there will be approximately 32 that advance to the next stage. Of the 6, 80% of them survive, and so we're going to round to about 5 surviving. Of the 24, 0 survive. Okay. Now, these 37 individuals are going to have offspring. Again, the one at stage 1 have 2 each, and the next ones have 4 each. So that's going to give us combined 84 individuals that are born that year, plus the 32 at stage 1, plus the 5 at stage 2, the 0 at stage 3, That gives us a population of 121 individuals. You can see that in this next time frame, the population has shrunk. And indeed, when we look here, we can see that our population starts at 100, it goes to the 138, drops down to the 121, and in our first time period, we had our population growth rate of approximately 1.38. It then drops down. In that next stage, it's going to be what? 121 divided by 138, which gives us a growth rate of 0.088. And so that's where we are here. And so what essentially is a lambda of a population that's not growing, that's just stable? Well, it's going to be 1. And anything greater than 1 is a growing population. Anything less than 1 is a shrinking population. Now, if you were to do this again and again and again, you'd get this graph. The population, although we had this one little decrease, begins to just sort of consistently grow. And it levels off at a population growth rate of about 1.32, which is pretty close to what our first year was. So we can use this lambda, this population growth rate, to basically calculate what the population is going to do on into the future. Okay, so now here at this point, got a little aside about some real live work that was done. And particularly it looks at sea turtles. And here's these cute little baby sea turtles. And this is what's known as this is a species known as the loggerhead turtle. And like many sea turtles, it's had declining populations over the last several decades for many reasons. And attempts have been made to help this species, to conserve it, to get the population numbers back up. Initial efforts focused on these little ones, and they of course hatch out on the beach and then quickly scurry to the ocean. So efforts were made to make sure that a lot of them make it into the ocean and that they're not eaten by things before they get there. But some studies showed that to really help this species, it's not the little ones whose survivalship is most important. It's actually the juveniles and adults. And so here are some of the results they had. Essentially, they're looking at the growth rate, what's known as the exponential growth rate, and we'll talk about that in more detail in just a minute, this value called R, which is related to lambda. And essentially, if you were to increase the survivorship of the hatchlings by 90%, it still does not help that population grow. That is, it does not get the exponential growth rate above 0. Okay, 0 for the exponential growth rate is just a stable population. Anything above population 0 is a growing population. Now you can see with juveniles, if they increase survivorship only 10%, again, doesn't really help. But as you get towards 50 and 90%, you can see particularly with 90%, that helps this population to begin growing. And with large juveniles, increasing survivorship of them 90% really does a lot to help this population. The same with subadults and adults. And so really it's the juvenile and adult stage and increasing their survivorship as much as possible is what helps. These sea turtles have somewhat of a type 1 survivorship curve. That is, they just naturally have high mortality of these juveniles. Not many of them survive. But under normal conditions, the adults, once they reach that juvenile and adult stage, they usually survive well and the population's okay. However, recently, not only do the hatchlings get eaten a lot as they're attempting to get to the ocean, but the juveniles and adults have had a really hard time, particularly from human actions, in particular shrimping boats. These sea turtles are often found where you also find shrimp, and when the ships come through and scoop up the shrimp, they sometimes scoop up sea turtles, and this ends up, for the most part, killing these adult sea turtles. So what has been developed are these things called TEDs, these turtle excluding devices. And here's this net that's connected to the boat, which is up this way. The back end of the net that's collecting the shrimp is down here. You can see this screen here, which has these, there's also kind of crosshatches there. So it has these openings that are plenty large for shrimp to get through, but the turtle kind of hits this screen, and then there's this opening that it's sort of forced out of. But the shrimp just, for the most part, just keep on going through the screen and down into the net, and they're captured. So these TEDs have been installed on shrimping boats, and at least initial results suggest that this is helping these sea turtles by decreasing the mortality of these juvenile and adult individuals, which is really the most important stage as we see for conservation efforts. So human actions can harm individuals, harm populations. Changes in environmental conditions more generally can as well. So here are these evergreen species that live out west, and so there's been an increase in mortality in these different locations, and you can see it's been much higher in the Pacific Northwest and around California compared to the more interior populations. And this is thought to be happening because of a drying out of the landscape, in particular, potentially due to climate change. In particular, in many of these areas, there's been less snowfall, which means less runoff in the spring when the snow melts, and less water in the soil, which makes it harder for these trees, thus increasing their mortality. Okay, let's go ahead and just start the next section, see how far we get. So we talked about this simple growth equation here. And by the way, you don't need to memorize these equations that we're going through, and there's going to be several more here, but you do need to know what the variables are and how to make use of them. Okay, so when you have sort of a positive growth rate like 1.38 or something like that, it sort of just gives you continuous growth. And when it continues long enough, it can lead to what we call exponential growth. You've probably seen a graph like this that just shows this. At first, the population size not increasing a whole lot, but as you go through time, just starting to explode like we saw in section 1 with the human population. The human population over the last 2 to 3 centuries has exhibited classic exponential growth. All right, and this one way of thinking of this form of growth is what's called geometric growth. And if we take our formula above here, if we know what the growth rate of the population is, we can use the size of the population in 1 year as we saw and calculate it in the next year. But can we use that value of lambda, that growth rate, to calculate further in the future, say year 10, or the number of individuals in year 20? How would we do that? Well, of course, we could just iterate this equation and calculate from times t to times t plus 1, and then do it again to times t plus 2, and t plus 3, etc., etc. But there's actually a formula that will calculate at any time in the future that we want. And this is our formula. So here's our growth rate, number of individuals at time 0, times t at some time in the future, and we take lambda and raise it to the power of whatever that year is. So I'm almost out of time here, but try this calculation. Use these values to try to calculate the population